Let us now talk about the cross-compilation toolchain. When programming a microcontroller, you have multiple level abstraction possible and multiple programming languages depending on the abstraction you're looking for versus the performance that you have. Historically, everything started with very small architectures that were programmed using assembly language. Every single line of your code was implementing a minimum fundamental operation to be done by your microcontroller. Now, obviously, as much as the complexity was evolving, we have been moving to higher level abstraction languages. And in particular, that was also the case for regular desktop systems with the C language, the C++, object-oriented programming, more recently Java, and so on and so forth. So currently, Java and C are the most trendiest languages for embedded systems. They have different objectives, right? Java is made to support retargetable solutions, so you have a virtual machine running your code no matter what the system is, while C will be used to provide very optimized, close to hardware languages, very optimized systems. In this class, we are going to use a C language because it is nowadays the most commonly used programming language for embedded systems, being yet fairly high level in abstraction, but providing you nitty-gritty details that you need in order to get the most of your architecture. So it's a very powerful and easy to use in order to express algorithmic steps. It only has 32 reserved keywords that you use in your programs. And we consider it today as a high-level assembly. Compared to the low-level assembly code that is very cumbersome, the high-level assembly C code will give you a very high level of optimization and performance while being very easy to write. So it does provide you with a low-level control of what the processor does. It piggybacks on very efficient compilers that are available for almost any single architectures, being it the GCC, C-Lang, and so on and so forth. And it provides a very high efficiency of produced code. In addition to that, the Optimism 3 in GCC provides you something that you will probably never be able to achieve with manual optimization. Yet, it is highly portable. You can program mainframes, big desktop, machine learning applications on data center farms, whatever. And at the same time, you use the very same semantics to program a very tiny microcontroller. So because of this versatility, this is our tool of choice for this class. So microprogrammed embedded systems are traditional devices that are not powerful enough to handle the compilation of their own program. Powerful and also resource limited in terms of memory. So you cannot run a compiler or development environment on them natively. So this brings in the question of cross-development platforms. A cross-development platform is a computer that will run a compiler and a development environment that is designed for another architecture. So you will use your computer and a specific IDE to do that in order to compile the piece of code that you will run on a different target. This code not being runnable directly on the machine that compiled it. So this is what we call cross-development platform, because an x86 architecture is going to compile a piece of code for an ARM architecture, for instance. It has many advantages, of course. It does provide very fast compilation of your applications, and it also gives you more opportunity for debugging and testing, because you're able to use the entire operating system and mainframe of your computer in order to run debuggers and evaluate and emulate the code you will be able to run on your embedded system, instead of implementing that on a very resource-limited structure. So what is a cross-toolchain for C language? So that will be a complete flow capable of generating a binary for the target platform we're considering, as well as validating it using an operating system and a machine that is not having the same architecture. This is the cross-compilation toolchain, and it consists of a set of tools running on the host machine. The first operation is always the pre-processing of the header files. By pre-processing, it typically replaces all the macros defined, it copy-pastes all the include files as part of a big chunk of C code. The second step consists of compiling your high-level C code into object files, .o. It is also possible to get the assembly code as a .s file if you prefer. Followed by that is the link operation, in which you will put together all the object files and you will end up with a final executable object that contains all the necessary object code. Finally, you will end up with the pack operation that will format your object file and put it in the right location inside your memory hierarchy. Indeed, you cannot have simply an ELF file that you'll put anywhere in the memory. It needs to be put at a certain location for your processor when it starts to start reading and jumping to the right memory location. This is what the pack operation does. So I mentioned the system code design framework, where you will have a first part on the development computer, the second part running on the hardware target. On the development computer, you will run your favorite editor that will help you to enter your C code. And this C code will be transformed into an executable file using the toolchain. You will then be able to load that on your development board. Now, the development board will be able to also run some debugger. That's the case with our STM32 discovery board. And this debugger will be able to connect with your development environment in order to put set points and watch data, for example, inside of your memory. In this class, we're using the Keil C-Based cross-compilation flow that contains the RMCC and RMASM in order to transcript C code into object file or assembler code into object files. The ARM-link binary that will combine all those different file libraries and object files into a .axf that will then be compiled into binary using the from ELF command. That binary will be able to be put actually on your final demo board. This will be the focus for our first lab, and you will learn how to practice this cross-compilation flow. Now, something quite interesting in this approach, even though the C code is not made to be retargetable very easily, we're still looking for compatibility during the compilation. So this is why we always have these two steps, where the first step, compiling the C code into object files using the ARMCC, and then the second part dealing with more like the link as well as the packing into the executable file. The first part is fairly machine independent because we simply compile some source language C code and use some multi-platform libraries. The second part, of course, will not be portable, not even among a compiler for the same architecture, because it all depends on your machine. The beauty, though, of this flow is that most of the time, some C code you will write for a given ARM core architecture can be easily translated to another ARM core architecture. To guide you a little bit more through the different steps of cross-compilation, let me show you an example where you compile a C code. So this very simple C code will get processed by your cross-compilation chain in the following way. First of all, there is this portion that are handled by the compiler. This is coming straight from the NC C subset. So this is your compiler deciding how to implement that on the machine. In addition to that, you have a couple of printf calls in this example that will simply link to C libraries for the target platform. So all of that can be translated from a target to another, simply having a different set of libraries. And finally, I'd like to simply point out the include file and defines that are the portion handled by the preprocessor which is also somehow part of the NCC subset.